And I will start with actually what had to be the final part of my morning lecture, and then I will continue with normal codiality measures and with one example of the one engineering. But I think it's good to go through this example because it's exactly, we can see in practice in one specific physical context all these notions of divisibility, non-divisibility, time local master equations, existence or non-existence of the inverse of the dynamical method. So we will do this. And this example I'm considering is an example of a microscopic exact approach. And it's a specific case in which we can solve exactly the dynamics, and we can have an analytical solution. So we have the form of the master equation in an exact way, and also the exact analytical expression for the solution. So it's obviously a very simple system, but it's often, very often used in open quantum system theory. It was perhaps the most used example when studying Markovianity, and it is an example of a non-unitary method, so there is dissipation. We will see later on a case of pure differential. So it's known also as the Janis-Cummings model for reasons. It's not a quantum optical Janis-Cummings model, but it's the case in which you do have a real environment. So as I said before, it's a microscopic system. So we are considering a two-level atom interacting with the electromagnetic field in the vacuum. And the total system, so the Hamiltonian for the total closed system is, as we wrote before, the sum of system, environment, and interaction Hamiltonian. And the system Hamiltonian is just a two-level system Hamiltonian, where naught is the Bohr frequency for the two-level atom. And the electromagnetic field is just a collection of infinite number of quantum harmonic oscillators. Now they are written in a discrete way when we pass them to the continuum later. And the type of interaction between system and environment is of the following form, where sigma plus and sigma minus are the inversion operators. So what happens here physically is that the atom can absorb one quantum, one excitation from the field, and this excitation is lost by the field in one of the modes indicated by K, and the opposite process. So there is only this interaction of exchange of quanta between the atom and the Kelvin field. Of course, for this model, it's easy to check that the total number of excitations for the total system is a constant of motion, and hence that's actually the reason why we can solve the example. So specifically, I will assume that the state of the environment is the vacuum of the electromagnetic field. So I can indicate, this is my notation for the vacuum of the electromagnetic field, so there are zero excitations in all the modes. And I indicate with 1K the state in which one photon is in one of the modes of the electromagnetic field. So actually, in the end, all the dynamics happens in a Hilbert space, which is for the full system, which only contains these states. So ground state for the atom, 0 photons in the electromagnetic field. Excited state of the atom is 0 photons, and ground state of the atom 1 photon in one of the modes of the electromagnetic field. And of course, it's also easy to see that when the state of the atom, if this is, for example, the initial state of the atom, well, nothing happens here for this system. And what we can do is that we can write down the state for the total system, so two-level atom electromagnetic field, so the total closed system, and we can just write it in terms of the states of the basis, psi naught, psi 1, and a combination of all the psi k's, because obviously the photon can be in any of the modes of the electromagnetic field. So look here, I'm actually looking at the dynamics for the full system. Okay, so I'm not yet focusing on my open system. That would be the two-level atom only. So of course we can write down the Schrödinger equation in the interaction picture. And I indicate here, I don't change notation, for example, for the Hamiltonian to indicate that it is in the interaction picture, but you can directly see it from the fact that now that the interaction Hamiltonian becomes time dependent. And in particular, the time dependency comes from the operators sigma classes, sigma minus, and decays, which acquire the time dependency once I pass in the interaction picture. And in particular, their time dependencies is simple to calculate, and one can immediately write them down in this way. So now I have, what I do next is actually to look for solutions of the total Schrödinger equation. Indeed, in this case, I'm solving the total system, right, until now. So I have I went back, yes, sorry. So I have the Schrödinger equation, I write psi in this form, I insert this expression here, and I obtain the coupled differential equations for the coefficients, C0, C1, and Ck, and in particular the coupled differential equations that I need to solve to fully know the dynamics have this form. Okay, so they are a set, an infinite number of coupled differential equations K containing all the modes. But what we can do is to formally solve the second one, so this one, so I obtain a formal solution for the Ck, and I plug it in here. So that eventually, from the formal solution for the Ck, plugging in the formal solution of the Ck in this equation, and passing to the continuum limit of modes, I will obtain an integral differential equation for C1 of t, which is this form. So it's an integral differential equation expressed in terms of what is known as the correlation function. And the correlation function contains J of omega, that is the spectral density that is basically describing the coupling between the two-level atom and each mode of the field. And then, of course, there are these terms that simply come from the operators in the interaction picture. So this object, the correlation function, is really, plays a central role and is related to the spectral density of the environment. Now, this integral differential equation for this specific system can be solved, and I will not do explicitly the solution. You can find in many textbooks, for example, in the Open Quantum System Theory book by Breuer and Petruccione, but there are many books in which you can find the solution for this differential equation. What you do basically is, in this case, is to use Laplace transform. So you Laplace transform this equation, you transform it into an algebraic equation, you solve it, and then eventually you have to, the difficult part is that you have to inverse Laplace transform to obtain the CFT. What is interesting is that if I now trace out the field modes, I will obtain the density operator for the system, for the two-level system only, which has this form. So the density operator for the two-level system only depends on the coefficients C1 and C0, of course. In particular, the only time dependency is from C1 of t. So one of the coefficients of the composition of the state for the full total system. And then, hence, if I have the analytical solution for C1 of t, then I have the exact dynamics for the density matrix of the system. Of course, when I say that we can always solve the integral differential equation for C1 of t, I was, in some sense, it's correct. Formally, I can always do it with a Laplace transform and then going back. However, an analytic solution is only possible for certain types of spectral densities. Okay? Otherwise, or for certain classes, actually, of spectral densities. Otherwise, you won't be able to solve analytically. And in particular, I will show in a moment the type of spectral density that we use. And in particular, we use it because it is physically meaningful. It is physically relevant in one of the experimental contexts, but also because it allows to give us an exact solution. But before showing the specific example of spectral density that we consider, again, in full generality, once you have the solution, which is this one, okay, for the density matrix, it's simple to write down the master equation. Here, as you can see, I'm proceeding back in the opposite way. Normally, I have the equation of motion and I have to solve it. Here I have actually the solution for the full system, in fact. and then trying to write down the master equation, that is the equation of motion of which that one is the solution. And it turns out that the master equation for the system has this form. So it has some unitary dynamics, of course, and these unitary dynamics, please notice that here I'm still, okay, there is one part missing, that is the, let's say, the free Hamiltonian of the system, because I'm still in the interaction picture. But basically what happens is that you add a time-dependent term, that is a lamp shift term, to the unitary dynamics, so that the frequency really, the atom fields is not just omega naught, the Bohr frequency, but is omega naught plus this S of t. It is the lamp shift. And this lamp shift depends on the coefficient C1 in this form. This is minus twice the imaginary part of this ratio. And then you have a dissipative part, which is in the form of Limblad master equation. So this is like a Limblad, Gorini-Kosakowski-Sudarshan-Limblad form, operatorial. From the point of view of the operators, as you can see, you have just sigma minus, sigma plus, and the sigma plus, sigma minus operator. So this is a Limblad form. But this is a time-dependent coefficient, and in general, we do not know whether it is positive or negative. However, in any case, if the derivation is exact, as we are doing, and we are not doing any approximation, this is always physical. I'm not doing approximations, I have no problems with complete positivity. And this is the decay rate. Of course, please notice, there is one point here, sort of a catch, that is the fact that actually these coefficients do not depend from the initial condition, simply because actually the solution in general, C1 of t, can be written as C1 of 0 f of t as a function of t. And because of this, this is the time derivative, sorry. This is C1 dot of t is the time derivative of C1 of t. So the ratio between the two, when I consider the ratio between the two, the initial condition here goes away. So this is neither the decay rate nor the lamp shift depend on the initial condition, as it should be, because the master equation should be independent from the initial condition itself. So it is definitely a non-Markovian in general, non-Markovian in the sense that I have not done any approximation of any type. And this holds in general, as I said. Now, however, we want to see the specific form, the specific time dependency of the coefficients, and therefore we choose a spectral density that is Lorentzian and picked in the on the Bohr frequency of the atom. Okay, so it's a Lorentzian spectral density. The reason why I say this corresponds to a physical example is exactly that this might very well describe one atom inside a cavity in a high-Q cavity scenario. So this is one of the modes of the cavities, the mode supported by the cavity, that is, in particular, the mode resonant with the frequency of the two-level atom. And here, this lambda coefficient allows me to change or defines the width of the Lorentzian. Now, for this specific form of the spectral density, you can calculate You can calculate here the correlation function, and it turns out that if you plug in here a Lorentzian, this is Fourier transform over Lorentzian, you obtain an exponential. So you have an exponential correlation function for this case, and you can solve with Laplace transform easily the solution. You can find out that the solution has this form here. So the analytic solution for the coefficient C1 of t has an exponential part which depends on the width of the Lorentzian. So there's this exponential factor, prefactor, front factor here. And then it's defined in terms of these hyperbolic sinus and cosinus functions, which in turn depend on this quantity R. Okay? This quantity R is the ratio between gamma naught and lambda. Gamma naught, if you remember the expression of the spectral density here, is in front of the spectral density, and it's like an overall coupling constant. The bigger is on gamma naught, the stronger is the coupling in the atom. So you have this ratio between how strongly coupled the system is to the field, and the width of the Lorentzian. Of course, please notice clearly some of you have heard about, I'm sure, about non-Markovianity or structured environments in other contexts. And very often people say a non-Markovian environment is a structural environment, meaning that it is, so in contrast with an environment where the spectral density is flat. If you have a non-structured, flat, white noise-like environment, then you have Markovianity, and the other way around. And please notice that if I increase this lambda here, I go more and more towards a flat spectrum. Okay? But it's not just how flat or structured is the environment that plays a role, but it is the ratio between how strongly coupled it is and how structured or non-structured it is that, as we will see in a moment, plays a role. Because here, this ratio R is what defines the behavior of this system. So, as you can see here, when R, so when 2R is greater than 1, this number here becomes negative. And so the square root then becomes imaginary, and the hyperbolic cosinus becomes a cosinus. And similarly here, please notice I have a similar expression here. So for R greater than, for 2R greater than 1, I will have cosinus and sinus here, and I will have some oscillatory behavior. This is what I call strong coupling, okay, because this is 2R greater than 1. But in fact, it's not just strong, it is really the ratio between these two parameters that these dynamics. And when this happens, if I look, for example, at the excited state probability of the atom, and I assume that the atom is initially in the excited state, I will see some oscillations appearing. The oscillations are caused, remember the excited state probability is just modulo squared of this quantity. In fact, this is real. Okay. So this is the square of this quantity, and so I will have the sinus and cosinus that gives me this oscillation. On the contrary, when 2R is smaller than 1, I just have some sort of some behavior which is not oscillatory, but contains sinus and hyperbolic sinus and cosinus. So behavior more similar to this one. Okay? Now, how is this related to the divisible versus non-divisible idea that we introduced before? I mean, what is the connection with divisibility and non-divisibility? Because you see here, we know also from quantum optics that what happens here in the strong coupling regime is that actually the excited state probability oscillates because the atom, being strongly coupled with a Lorentzian on resonance, exchanges energy with the cavity, with the mode of the cavity which is resonant to it. So it really exchanges excitation. So it goes up because really there is this exchange of one quantum of excitation, which doesn't happen in the recoupling case. Now the connection with, and so you can say intuitively that this exchange of excitation is, there is something coming back from the environment into the system. In this case, it's really a quantum of energy physically. Okay. So, and this is like non-Markovian in this sense. Okay? There is something that goes back in the system. The correlations are so strong that something goes back in the system. So, but what is the connection with divisibility or non-divisibility? I think I have here the expression. I've written it down because I didn't have it in the presentation for the here it is. To understand the connection with divisibility or non-divisibility, we have to go back to the master equation, which is this one, okay? And we have to go back to this object here. Because if you remember what I said in my previous lecture, we could characterize divisible maps as those maps which have a GK, Saborini, Kosakowski, Sudarshan, Lindblad generator with always positive gammas of T. Okay? So we know that there was really this characterization. We know that the dynamics is divisible anytime this is already in the form, in the Lindblad form, but we have to make sure that this gamma of T is also positive to talk about divisibility. And so, of course, you have the analytic expression for this coefficient, and the form of this coefficient is the following. I will write it down here. So, gamma of t is equal to what's gamma of lambda, hyperbolic sinus 2 square root 1 minus r, and denominator is 2r hyperbolic cosinus r, and then I have lambda yes. So you can see, actually, it's very simple to notice that whenever 2r is greater than 1, so in the so-called strong coupling regime, well, actually, let's do first the other one. When 2r is smaller than 1, okay, then we do have still the hyperbolic sinus, hyperbolic cosinus, and all this expression can be easily checked to be always positive. So gamma of t is always positive in the weak coupling, so-called weak coupling regime, which is the regime in which I observe this behavior. On the contrary, when 2r is greater than 1, exactly the same as I was saying here happens. You start having this sinus and cosinus oscillatory behavior, and as a consequence, gamma of t becomes temporarily negative. If you plot it, you will find that some intervals of times in which gamma of t is negative, and therefore the dynamics is non-divisible. Okay? So if you remember what I said before, I considered the definition of Markovian versus non-Markovian to be equivalent to divisible versus non-divisible. Otherwise, I talk about Markovian semigroups. But if you want to generalize a bit, then this is what I just said. And here it's exactly what happens. Okay, it's precisely the same thing. So we obtain non-divisible dynamics whenever the decay rates are negative, and hence the dynamical vector is non-divisible, and otherwise we have Markovian dynamics, and we do not have oscillations in the excited state probability. Now there is a catch, and this is very important at this point. And the catch is the following, that in fact, if you study this gamma of t a little bit in more detail, you will find out that, let's see if I have the definition here, you will find out that actually there exist certain times at which, and in fact this times corresponds to when the probability, excited state probability goes to 0, in which these decay rates diverge. This happens here. So this happens only in the non-divisible case. In the divisible case, it's all okay. But in the non-divisible case, there are some points corresponding to the zeros of C1 of t, in fact, for which the decay rate here diverges, comes infinite. And well, this simply means that actually, strictly speaking, this Maxwell equation does not exist in the form that I wrote before. Right? And this is related precisely to the fact that the dynamical method in this regime does not have an inverse. It's not invertible. You lack this bijectivity property, so it is not invertible. In this example, this is not invertible, so strictly speaking, doesn't even make sense in general here to talk about the propagator being completely positive or not. Okay? Because I don't have it. The propagator was, if you remember, defined, I called it before BTS, and it was lambda t, lambda s minus 1, but this does not exist here. Now, why then I'm talking about this example, which actually I couldn't talk, strictly speaking, about divisibility or non-divisibility here, because this is actually more a mathematical problem than a physical one. Why? that I only chose in the spectral density, let's see if I find the spectral, yeah, again, this exact resonance. Okay. If I instead do not choose an exact resonance condition, but at my peak of, the peak of my Lorentzian, I can call it omega c. So there is a certain detuning between the Bohr frequency. It can be as small as you want. Okay? Between the two levels, the Bohr frequency of the atom and the peak, omega c is the peak of the Lorentzian, now the Kelvin mode if you want. Then whenever this happens, actually everything works well. The solution is a little bit, tiny little bit more complicated, the analytical solution. But what you can see from the analytical solution is simply that, well, first of all, the C1 of t is not a real number anymore, it becomes a complex number. The gamma of t is always well defined. And also in that case, you have precisely the same thing. You have divisibility or non-divisibility depending on whether the decay rates are positive, gamma t is positive or negative, the solution is perfectly defined, and so on and so forth. So it is really, for me, it's a mathematical thing, because exact resonance is not, okay, I would say it's not physical, I mean, it doesn't really exist, okay? And this is something that in any case is, works well. So there was another important point that I wanted to make, yes, make here. But even in the case of exact resonance, the master equation does not exist. For the case of exact resonance where I lack invertibility, but the solution does. Okay? The solution is perfectly physical. Okay? The solution is perfectly well defined. What does not exist is the master equation in this form. I have no problems with the equation. Okay? But I cannot really speak of divisibility or non-divisibility in that case, because that is based really on the positivity of this object. Okay? So I really wanted to show this example to illustrate some of the ideas that we have discussed before. So are there questions on this part? If you want to move on to materiality? Yes?
Well, on this last thing you said that there is a solution, but you can't find a master equation. Does that mean that there might be some other form of master equation for which that solution?
Probably, I don't know. I mean, actually, I can ask some of you yes.
Yeah, you can go to the non-local picture.
Yeah.
And you have then perfectly regular numerical functions.
So the form of the master equation would be more of this, because if you remember when I mentioned in the first part of the lecture, I mentioned that when we consider these time local generators, we are not considering all possible types of master equation. I'm excluding some types of master equation. In particular, I'm excluding types of master equations which have this form. Okay, I could have, for example, a dot of t. Just a dissipator, actually. I will write only that. I have an integral between 0 and t, and then I can have a L of s, and then I can have some k of t minus s, for example, ds. So obviously I need to apply the rho s. Yes. So here, this is the master equation. So this is it could be just an example. It could be the Liouvillean for example, Lindblad form, find s. Then I have some kernel here. It could be an exponential memory kernel. But what is most important is that here, the density matrix at time s is inside the integral. Okay? So I don't have, well, normally, before we noticed how we were mostly dealing with situations of this type. Okay, but here I have, let's say, this type of memory kernel master equations, and this is more general. And for example, this thing. Are there other questions? Yes.
A question about the spectral density.
Yeah.
Sorry if this is elementary, but so you have some choice.
Yes.
You showed here a concrete choice.
Mm-hmm.
What does that choice correspond to at the when you first described the system? Is it something in the parameters in the Hamiltonian or in
Yes, not in the initial condition, but in the, what do I have? I lost it. Not in the initial conditions, but here, in the, oh, here, okay. Sorry. So I have this in the microscopic model, which was here. In the microscopic, yes. So here in the interaction Hamiltonian, I have these coupling constants that says how strongly my two-level atom is coupled to all of the modes. When I write down now here I wrote it directly in the continuous limit, but basically I will obtain, when I plug in this here, I will obtain something which contains the integral differential equation will contain this GK modulus squared. And this object is what eventually, with some factors, becomes the spectral density. So they're the coupling, microscopic coupling in the interaction Hamiltonian that defines spectral density. Other questions? Yes?
So you're not certain when this decay rates diverge, no?
Yes?
They will appear inside time integrals, as you say.
Like, you mean there? Okay,
In the dynamics, the dynamical market is kind of a time order integral generator. So even if the things diverge, can we not be happy enough with this integrable divergence?
well, the thing is that I think that in any case we are happy enough because we do have the dynamical time. We do have the time evolution. We have the rho of t, which is okay. I mean, the lambda of t, the dynamical matrix is defined. It's not. It's the inverse which is not defined. So yes, I mean, we are. The question is we cannot write directly the master equation because it doesn't have. Or we cannot write it in a time local form. We must write it in another form, a more general form. And also, it's more tricky to talk about divisibility or non-divisibility because, well, we don't have the inverse, the existence of the inverse. So divisibility or non-divisibility is defined in terms of complete positivity of this propagator. No more questions? Time. Okay. Doesn't matter, but it's a useful example to fix some ideas. So let's go now to non-materiality and to information. So this first of all, a little bit historically, goes back to some discussions that I think started maybe around 2008. And the discussions were based on the following question. Okay, nice. We have these definitions of divisibility or non-divisibility, Markovianity or non-Markovianity based on these properties of the dynamical map. But is there any way of interpreting them physically? So people say associate non-Markovian dynamics to some sort of memory effects, to some sort of can we quantify these memory effects? Can we have some physical understanding of non-Markovianity? So is there a way of interpreting it that is not simply mathematical, okay? Not simply based on this mathematical property of the dynamical net? So one of the first proposals was to study this idea or this concept of Markovianity or non-Markovianity in terms of information flow between system and environment. Okay? So the way in which quantum information on the system is lost when the system interacts with the environment. Now the question, of course, is that when you start doing this going along this road, you may ask, okay, there are several ways of quantifying information. How do I use a proper quantifier of information? You may think that, for example, von Neumann entropy might be one of the first ideas that come to mind to quantify information of the open system. Well, it turns out that not only you want to describe things in terms of information flow, but also you want to do it in a way that is consistent, or that is not consistent, but in some way related at least, to the notion of Markovian or non-Markovian that is known from the theory, that is divisible or non-divisible, if not the same. You want to have something that is connected to what has always been considered Markovian. So, one of actually the first proposal to describe non-Markovianity in terms of information was based, I think it's from 2009, by Breuer, Line and Pilo, and was based on a quantifier information based on distinguishability, so state distinguishability, so distinguishability between states. Again, this is a quantum information idea. They expect to this picture I took directly from Winston and Chung. So more information, less the connection between the amount of information we have on states and how how much we are able to distinguish between them, which is quite intuitive from this calculation. This connection can be seen also in terms of a simple game between Alice and Bob. So we'll introduce a state distinguishability soon in mathematical terms. But you can imagine the following thing. So Alice can prepare two states, rho 1 or rho 2, with 50% probability. She sends them to Bob. And Bob has to guess which one of the states. And it turns out that the maximal success probability that Bob can achieve using an optimal strategy is expressed in terms of a quantity that is the trace distance between two states, rho 1 and rho 2. So trace distance is defined. This is the trace norm of the two states, rho 1 and 2. You have two states, rho 1 and rho 2, rho 1 minus rho 2. 1/2 of trace of the norm of rho 1 minus rho 2 defines the trace distance. And hence, there is this connection between this state distinguishability and trace distance, which is used to quantify information on a system. And the first proposal exactly uses trace distance to quantify non-Markovianity information flow. The obvious properties of trace distance are that it is always defined between 0 and 1, and when the trace distance is 1, then you have actually the maximal probability, and then it's 0, so when the states are, this is when they are maximally distinguishable, this is when they are distinct. So, this is what they started to do. Okay? What was their aim? To use this quantifier to study information exchange between system and environment, so using the trace distance. And the idea is the following. Here, I'm just recalling, actually I will go very briefly here because we have already discussed these things. The dynamical map and the divisibility conditions. Okay. I'm just rewriting them. This is the propagator of V. Sorry, because I simply changed the slides, and so now I'm using a different notation. These are the precisely same things that we noticed before. And we know again that whenever the propagator is completely positive, then the dynamical map is strictly divisible, and we call it Markovian. Whenever it is in the case in which it's not completely positive, then you have indivisibility and non-Markovian elements. And we want somehow to connect these with the idea of trace distance, with the behavior of trace distance. And the connection comes from a property of trace distance that is called the contractility of trace distance. So, consider two initial states of a quantum system, rho 1 and rho 2. Trace distance is contracting, meaning that the distinguishability between any pair of states is greater than the distinguishability of the evolved state. Right? Because remember, phi t now is my dynamical map, so it's completely positive and trace preserving. This happens for the action of any quantum channel. So what this tells me is that as the state evolves, if I consider distinguishability between initial states and I compare it with the distinguishability of the evolved state, the distinguishability of the evolved state is always less than the initial one, okay? For any physical dynamical map. So this means also remembering the interpretation of trace distance in terms of quantifier of information, that because of the presence of the environment, I'm losing information on the system. So I send two initial states through quantum channels, and in fact through dynamical maps, because if you want the length of this channel tells me how long time the system has been subjected to to the environment, and in the end, the distinguishability between the two states will be always less. So this is a way of saying that information has been lost. However, if I look at the propagator, so the intermediate map or propagator, the propagator may not be completely positive, completely positive. So what happens is that I can have two different scenarios. In the first scenario, the trace distance decreases always monotonically. But in the second scenario, the trace distance may temporarily increase, never more than the initial value, obviously, but may temporarily increase in time. And if you remember the contractility properties, these can only happen, so a non-monotonic decrease in trace distance can only happen if I use complete positivity on the intermediate. So what happens is that a situation, if I look at trace distance, a non-monotonic decrease of trace distance tells me automatically that the dynamical map is non-divisible. This is not an if and only if condition, it goes only in this direction. The difference between these two scenarios in terms of information loss is that here, information is continuously always lost in time, while in the second case, you can have some periods of times in which you have a partial regain of information on the system, and then it decreases again. So you have, the system is not just losing information, it can gain temporarily and then it goes back. And this partial increase of information is a signature of memory effects. So memory effects, and hence non-Markovianity, physically are associated to what is called information backflow. So this idea so the key, the first one is of the realization of how information backflow can be associated with Markovianity. And of course, okay, this is the reference of this paper from 2009. And I already mentioned that in this case, information is always lost, and in the other case, information can be partly regained, and you have this memory effect. So you have information backflow in this case. And of course, you can also, nowadays, this idea of non-Markovianity is quite widespread, but it's also true that if you look at different communities for condensed method or thermodynamics, they really consider non-Markovianity as different things. It's not still, let's say, a question of language very often. Okay, one can ask, how about the time scale? How about recoupling? How about, Limlat master equation? Again, the connection is what I was mentioning before with visibility, that is the following, okay? Whenever the dynamical map is CP divisible or divisible, so I call it divisible here, so I'm calling it divisible, the master equation is of Guarini-Kosaborski integration form. This is a simpler K version with always positive decay rate. And in this case, yes, sorry, yes. And in this case, the trace distance is always monotonically decreasing. If I have non-monotonic behavior, then I can imply that the dynamical map is not CP divisible, and therefore the master equation is not Guarini-Kosaborski equation. So this is the unique sort of connecting point. So, if you want in a simple way, and there are here some reviews, two recent reviews on generally on the Markovianity in terms of information flow, with much more information than what I gave you now. So what we do, one of the ways of doing it is really looking at the behavior of trace distance. Now, before I continue with some more specific examples, do you have questions on this point? Yes.
So you mentioned the distance, but there's a team of quantities that are also contracted, right?
Yes.
Does it not consider more?
Yes.
Or?
Okay, that's will directly lead me to this other, I found it, presentation that is here, which is, okay, let me just show you this. Okay, there are indeed not just stress distance, but there are a number of other quantifiers. There is mutual information, they are all contracted. Mutual information, coherent information, channel capacities in some cases, fidelity, entanglement with an ancilla. So indeed, what has happened, and here I'm mentioning few, not all of them, what has happened is that people have started to use them also to quantify memory effects, because they all have the same property, and you may ask, okay, isn't this creating confusion? Okay, they are not equivalent. The only connection is that divisibility implies monotonic behavior because of contractivity, but that's the only, and therefore in some sense they are witnesses of non-Markovianity, because whenever you see an increase in this information, some oscillatory behavior somehow in all of these quantities, then you can conclude that the dynamical map is non-divisible, that's fine. So they are witnesses of non-divisibility, hence of non-Markovianity, but they are not equivalent. In some cases they coincide. Coinciding not numerically, but in distinguishing Markovian versus non-Markovian. And the idea is that, well, generally they may be useful in different contexts. So if you are interested, for example, if you ask yourself, assuming that I have ability to control my environment, to do reservoir engineering, and to engineer a more non-Markovian versus the Markovian environment, okay, you may ask, okay, do I want to have a more non-Markovian environment, I don't know, for some quantum, for example, for metrology, okay? Then maybe you use Fisher information, okay? Or for state estimation. Then you use maybe Fisher information, you don't use this. So depending on, or if you may be interested in the same question, but for protocols of quantum codification, then you may use the channel capacities, okay? So depending on the type of problem you want to tackle, and again, the question again is, can I use these memory effects to my advantage when noise is present? Okay? Because intuitively, the idea is that, well, if something comes back during the time evolution, so I have a certain quantum system. The quantum system is losing information due to the environment. And you may think, because of this information is continuously lost, it's better to act as fast as possible. Okay, so I want to make my communication protocol or my estimation protocol, whatever, as quickly as possible, because in this way I will have a higher whatever Fisher information or whatever parameter I'm using. But the idea is that actually this is not true in the non-Markovian case, because in the non-Markovian case, because you have these revivals, it might be better actually to wait longer, because something may come back. Okay, so you may change the length of the channel depending on the memory effect. So let's say that this intuitive idea that, okay, because of the presence of noise, we must operate in the shortest time scales is only true for Markovian cases because of the contractility, but it isn't in the non-Markovian cases. So you can also imagine to tune your parameters or your memory effects, so if you have a certain fixed length for your channel, then you may imagine to tune it in a way to maximize the backflow of information at your output. So there are a lot of ideas. And different quantifiers may be useful for different purposes. Okay, it was a long answer, but anyway. So there was another question? Yes?
I was wondering, what about the two states that you choose to check if the evolution is not
Very good point. Indeed, I didn't finish what I had to say. Yes, very, very good point. So, I'm happy that you asked this question because I actually did not say what I had to say. So, the Markovian versus non-Markovian characterization of a dynamical map must be a characterization of the dynamical map. It cannot depend on the choice of states. Okay? So indeed, what one does when studying non-Markovianity is to optimize the behavior of trace distance over all possible pairs of initial states. So you have to find the pair of state which maximizes the backflow of information. Okay? So obviously this is a complex, generally a complicated problem. Sometimes you have some exact ways of calculating it exactly, but it is always an optimization over all the pairs of initial states. So, but obviously, if you're only interested in finding out whether the dynamics is Markovian or non-Markovian, and you have some intuition on which pairs of states might be the one leading to information backflow, then what you can do is that it is sufficient that you find one pair of state for which you obtain information backflow. And in this case, well, you already can say it is non-Markovian. Obviously, what is more complicated is to verify Markovianity, let's say, in this sense. But anyway, but of course, in general, it is a property of the map. So in general, it's not just sufficient to have two pairs of states, but you have to do over all pairs of states. Questions? And I have probably less than 10 minutes. Okay. Less than 10 minutes. I wonder what can I do in less than 10 minutes. Yes, okay, I could in particular, because what I wanted to do, yeah, maybe I can elaborate one moment on the idea of reservoir engineering that I wanted to define before, and then I can tell you one thing about how to engineer reservoirs, one example of how to engineer reservoirs. So, in the past, the most common idea about noise or environment is that actually this sentence is written in a lot of papers. Decoherence is the major enemy of quantum technology. This is like was really extensively used because, of course, it destroys quantumness, and hence, if you have a protocol that relies on quantum properties such as entanglement, that is bad. Okay? But soon after, I think, and maybe even in the present, people sort of started to change their attitude. Okay, know your enemy means know the coherence in this case and how to model it, but perhaps even exploit your enemy. So there have been in the past a huge number of proposals showing that actually we can use the coherence of the environment in this case to protect or even to induce quantumness as stationary states. Maybe in the future we start loving our enemies, so we could even imagine to start exploiting and changing the coherence in order to maximize quantumness. In some sense, reservoir engineering can help in this way. And there are two specific examples that I wanted to give. I will not be able to give them both on reservoir engineering, both of actually originally there were three, but then again. And in particular, I can talk briefly about the dynamical decoupling idea. 5 minutes? Yes. 6. 1. Okay. Obviously, the preliminaries you have heard already. But the key idea is the following. This is related to a result mostly obtained by Carl Abdis. So the idea is to use dynamical decoupling as a tool of reservoir engineering and to study how this is connected with non-Markovianity of the environment. And in particular, so you can ask different types of questions, but one question is, in absence of any dynamical decoupling, okay, we may have a Markovian or a non-Markovian environment, and the question is, which one of the two is best to obtain maximal efficiency of dynamical decoupling? So to maximize the efficiency of dynamical decoupling, is it better if my environment is Markovian or non-Markovian? You can also ask a different questions. We also studied the question, how does the dynamical decoupling induce non-Markovianity? Okay, what is a different. Okay, and the model that we use is a very simple model of pure dephasing, where the dissipative part is again in that form with a time-dependent coefficients. You only have dephasing here. The diagonal elements are the same. The off-diagonal elements decay according to a certain decoherence factor, this gamma naught of t, which is just the integral between 0 and t of the dephasing rate. Okay? In particular, you can directly, so this is an exactly solvable model. It's microscopic, and you can solve everything exactly. And in particular, you can write down the master equation in terms of the spectral density. Here I call it I because in general it's a T temperature environment. You will have also a thermal factor. It's hyperbolic cotangent containing the temperature, but it doesn't matter. So you have an analytic expression for everything. And the class of spectral density considered is of ohmic type, so they're proportional to omega. So S is a ohmicity parameter with a cutoff that is exponential. And in this case, what is interesting for this model is that by changing S, the ohmicity parameter, you can go from Markovian to non-Markovian. And here, in particular, you can, for this specific model, an interesting and important idea is that divisibility or non-divisibility coincides with the monotony, with BLP or with the trace distance Markovianity or non-Markovianity. They are the same things here. They are equivalent. So, okay. So, and in fact, all the Markovianity measures give the same border between Markovian and non-Markovian. They're all equivalent for this system. What we do is that we use the trace distance measure, which is defined in the following way. So we have the derivative of trace distance in time. It's called the information flow. And as I was mentioning before, the measure itself of non-Markovianity must be obtained optimizing over all possible pairs of initial states. So you look at the period intervals of times in which the information flows back. So the information flow is positive. You sum them up in this interval, and then you optimize over all the possible initial states. So this gives the measure itself. And in this case, the optimization is analytical. You don't have to do anything numerical. And in particular, it has the ball quantity has this form. What we have done is, in particular, you can do the calculations and you can study that this specific model is non-Markovian only when S is greater than 2 for a certain range, otherwise it's Markovian. And we study the interplay between dynamical decoupling and